Alright gang, here we go. Electron configuration. Now this is hopefully where uh, all that quantum mechanics stuff that we just talked about, that you're probably still like, why the heck is this all important? All that stuff, this is really where we start to see the purpose behind all those things we were talking about, especially that periodic table that we colored for your checkpoint. Okay, so go ahead and pull that out next to you so you can look at that while we're working through electron configurations. Okay. Now the whole idea about electron configurations is it's a way for us to keep track of what orbitals our electrons are in. Okay, and it has a specific notation system, meaning we're going to write it down in a specific way. Okay, so electron configuration is the arrangement of electrons in their different orbitals. Okay, and there are three specific rules that you have to know. Okay, off-bow principle, Pauli exclusion, and Hund's rule. Now, the off-bow principle, yeah. Okay. So pause the video real quick so you can jot all these things down, and then we'll talk about them. All right. So off-bow principle says that electrons occupy orbitals of lowest energy first. So when you're putting electrons in, they're always going to go in the n equals 1, and then 2, and then 3. Okay, that's the off-bow principle. Pauli exclusion principle says that each orbital can only have 2 electrons. Now you already knew that from talking about quantum mechanics in the video before, but that's Pauli exclusion principle. So when you're filling these guys up, your s orbital, that's an n. Your s orbital can only hold 2 electrons, right? Because there's only one orbital within that s. Okay, but p's have 3, so it can hold 6 electrons, 2 in each. Remember talking about all that? And then Hund's rule says that as we're filling up these orbitals from lowest to highest based on off-bow principle, you're going to fill up that orbital until each orbital has 1 electron in it that all have the same spin. And then you'll start going in and putting the second orbital in, or the second electron within each of those orbitals. Okay, it'll make more sense, but we'll do some practice problems here. All right. So here's our electronic configuration map of the periodic table. This is pretty much what we drew, right? Okay, we've got our s orbitals over here. They're in yellow. Our d's in yellow, or our s's are in red. Our d's are in yellow, and our p's are green. F's are like this brown color. I don't know. Anyway, so longhand notation. So the way we're going to do this is you're going to have, there's 3 parts to each longhand notation. There's going to be a number, and then a letter, so I'll just put a capital A, and then a number up top. Okay? Now this number here is going to tell you what n level. Okay? So that's the 1, 2, 3, 4, 5, 6, 7 that walk down the line this way. This value here is going to tell you if you're in an S, P, D, or F. Okay? And then this value here tells you how many electrons there are in that value. Okay? So we'll say number of electrons. Alright, so this first number tells us what n level we're at. The second level says what shape of orbital, S, P, D, or F. And then this last number tells us the number of electrons. Alright? So, for example, if I wanted to talk about helium, helium is this guy right over here. Maybe I'll change colors real quick so it's easier to see on the picture here. Okay, so this right here, this is helium. Okay, so to do the longhand notation for helium, where we write out first, we got to write out, well, we're on the n sublevel. Okay, so just so you know later, helium, right? We're on the n sublevel of 1, and it's in S, right? And it's got 2 electrons in it. 1 here, and the second one's over here, right? So 1s2. So that's the longhand notation for helium. Right? We'll do a lot of examples here in a second. A couple of things I want you to pay attention to real quick is these n levels follow down here, just like these numbers here, for the reds and the greens, for the s's and the p's. But when you get to the d's, their numberings get funky. Okay, so D, this first row of D is going to be 3, and this first row, or the second row, it will be 4, and then 5, 6. So it lags behind these over here, okay? So that's 3D. Oh my goodness. Let me erase some of this so it doesn't look so junky. Alright, so this is 4. Alright, and then when we're in the F's, this guy is actually a 4, and this is a 5. Alright, so they kind of lag behind again. Alright, so keep that in mind. Now, the other way you need to be able to write electron notation, electron configuration, is by noble gas. It's the shorthand. Alright, so meaning it's a little easier. So we use it all based on the noble gas that came before. Alright, so this row here, or column, excuse me, is all the noble gases. Okay, they're very stable. So helium, neon, argon, etc. Okay, and the way these work is almost exactly the same. The only difference is we're not going to start at n equals 1. You're going to go to the noble gas that came before it. So I'll call this capital NG, and you're just going to put a bracket and write in whatever that noble gas was. Okay, that came before it. And then you're just going to do the same thing for everything else. You'll put your number for your n level, you'll put your SPD or F, and then you'll put the electrons up here. Alright? So keep those in mind as we do some of these examples on these next couple of slides. So we're going to figure out together the electron configuration for nitrogen. Okay? First step is to find nitrogen on the periodic table. It's right here. So if you want, you can go ahead and label the periodic table like this. Okay, so now we see that nitrogen's on the second sublevel. But since we're doing longhand, we have to account for all the electrons. So we have to start with n equals 1. Okay, now if you look at your periodic table from before, that first row, hydrogen and helium are both in S. So we're going to write 1s2 for those first 2 electrons. Now we're in the second sublevel, so now we're going to put 2, and then these guys here go s2, right? Because both of those are filled, because we have to get all the way over here to nitrogen. We're still on 2, but now we're not in s's, we're over here, and these were p's, okay? And then how many electrons are we filling up in the p's? Well, we have 3. So 2p3. So this is nitrogen. This is the longhand notation for nitrogen. 1s2, 2s2, 2p3. One way you can double check yourself is by taking these superscripts, or these numbers up here, and if you take all 3 of those and add them together, it should equal the atomic number of nitrogen. Okay, so 2 plus 2 is 4 plus 3 is 7, and nitrogen 6, 7, so we're good. Okay. Now the noble gas notation, remember we're going to find the noble gas that came before nitrogen. So we're going to look back up a row at the noble gas, so that's helium. So we're going to put bracket helium. Alright, so that bracket stands for everything that came up to helium. In this case it was just 1s2. But as you can imagine, as you get farther down, xenon will save you a whole lot of writing. Okay, so helium, and then now we just do 2s2 because we're here at the second row, and then 2p3. Yep, and that's your shorthand notation. Notice that it's exactly the same thing, only we saved ourselves writing all of the n's before the levels that we actually care about. Alright, the longhand notation for fluorine. First step, find fluorine on the periodic table. It's right here, number 9. Okay, so we start right here at this row. So we've got 1s2, and then we're in the second row, so 2. This is all the s's are full, so we'll write 2s2 because that s has 2 electrons completely full. Now we're in the p's, 1, 2, 3, 4, 5. So we're still in the second row, but now it's a p, and there's 5 of them. So we can double check ourselves, 1, 2, 3, 4, and then plus 5, 9. We get 9 as the atomic number for fluorine. Now sodium, 1, 2, 3, 4. Anyway, So sodium is way down here, number 11. Okay, so we're going to have to write a little bit more. So all of the first level is full. All of the second level is full. So we get 2s2, 2p6. Now for the last one, we're on the third row, S, but just the first one. There's not two, there's only one. So that's sodium. 1s2, 2s2, 2p6, 3s1. Okay? Alright, now we're going to write the noble gas notation for krypton. Okay, krypton's way down here. Okay, it's a noble gas. So we're going to use, remember, we're going to use the noble gas that came before it. So that's argon. So we're going to say bracket argon. Okay, and then we're just going to start here. So this is the 1, 2, 3, 4th row. Okay, so we're on 4. All of our S's are full. So that's our 4s2. Now remember what I said. This right here starts with 3. All of these are going to be full. Okay, so that's a 3D, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So 4s2, 3D, 10. And now we're back in the 4s. Okay, 1, 2, 3, 4, 5, 6. So 4p6. Alright? And so that is the noble gas notation of krypton. Now you could imagine if we didn't have the shorthand notation, for argon you'd have to write, so before all this you'd have 1s2, 2s2, 2p6, 3s2, 3p6, and then you could start with the 4s2, 3d10. Alright, now copper, right here, number 29, okay, so it has the same noble gas that came before it, argon. Okay, so bracket argon, and it's going to start the same way, 4s2, and then we're in the 3Ds, and it's not all the way full. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 4s2, 3d9. Okay? So that's the shorthand electron configuration for copper. And that's really all the tricks to it. One thing that you want to make sure you do is understand, so our D's will be this 3, 4, 5, 6, right? And we talked about how these F's start over at 4. So 4 and 5. But then remember that the numbers don't get affected in the P's over here. Okay, so these are still 4 P's. These are still 5 P's, 6 P's, 7 P's. Okay? So the delayed numbering only affects that particular set of orbitals, D's or F's. Alright? Cool. Well, do some of the practice problems, check your work. Remember, the keys are posted on Google Classroom and up there next to the fume hood. And let me know if you have any questions. And there's just a regular old checkpoint for this guy.